Good afternoon. I would like to thank the organizers for the kind invitations. Pleasure to be here. I'll talk to you about multicriticality and topology in the phase diagram of spin-orbit coupled electronic chain. This is a work carried on in collaborations with these guys here. I don't think this is actually working, the pointer. No, but the laser, okay, good. So, well, first of all, a little bit of a disclaimer here. This work is a little bit shifted from the topics that have been discussed today. It's not about 2D materials, nor is it about spintronics, but nonetheless, spin will play a crucial role in the results that I'm gonna show you, so it's not so far away. So first of all, let us remind ourselves what quantum phase transitions are about. So the standard classification has that quantum phase transitions are basically fall in two big classes, those which are governed by symmetry and the ones that are governed by topology. In the symmetry big class, we have two main cases. The standard Ginzburg-Landau-Wilson kind of quantum phase transitions, which are driven by a broken symmetry. So some kind of symmetry is spontaneously broken in the ground state of the system, and this distinguishes two different phases of the material. And you also have the confined quantum criticality, which happens when you have two different types of symmetries, which are broken in the two different phases of the system. So the standard textbook example is a two-dimensional system. In one side of the phase diagram, it's an antiferromagnet. In the other side is a valence bond solid. And the types of symmetries which are broken in these two phases are completely different. And then you have the topological phase, quantum phase transitions, in which the defining feature is a topological invariant, which takes different values on both on the different phases of the material. So let's also remind ourselves that the common signatures of quantum phase transitions, be the transition a symmetry breaking type of transition or a topological phase transition, we always have some common signatures, which one of which is that the gap closes at the transition. So the two phases are defined, they have well-defined gaps between valence, between, you know, the highest occupied band and the upper band, and this gap closes at the transition. Another common signature of a quantum phase transition is a non-analyticity of the ground state energy. So here is just a very rough cartoon. If you plot your ground state energy as a function of some parameter in the system, at some either the ground state energy itself or one of its derivatives develops non-analyticity exactly at the phase transition point, right? Typically, this occurs for the second derivative of the ground state energy as with respect to this parameter. So mostly we have second order quantum phase transitions. Okay, so with this very brief introduction, I come to the model in which we're going to be discussing. It's a 1D lattice, which is half-filled, and there are only three ingredients: hopping, two types of spin-orbit interactions, and spatial modulation. So the tight binding type of Hamiltonian that describes such a system has a very simple form. This coefficient here in front of the creation and annihilation operators is modeled in this way. We just have a hopping term, a rush by spin-orbit interaction. Here I'm assuming a chain running along the x direction. So this Rashba terms couples with the sigma y Pauli matrix. And then I have a gamma d, which controls the strength of a Dresser-Hall spin-orbit interaction in the wire. So these three parameters, T of n, gamma R of n, and gamma D of n, they are all modulated in space. So n here is the site index along the wire. So all of these three parameters can be modulated in this way, where x here takes on either T or gamma R or gamma D in each case. So we have a uniform component and a modulated component, and this modulation goes in this way. And the important parameters here are the wave number of this modulation, this Q, and the phase shift. And so, as I said before, T, gamma R, and gamma D are the hopping amplitude, the Rashba and Dresser-Hall's spin-orbit interactions, respectively. So, some years ago, me and collaborators, we have looked at variation of this problem, which is the previous Hamiltonian plus electron-electron interactions. This kind of model can be realized in a quantum wire, a semiconductor quantum wire, subject to some external electric field modulated in space, periodically modulated in space. And we have found that this kind of system, so if you look at the bands, so these are spin-shifted bands. The spin shift comes from the spin-orbit interactions. And due to electron-electron interactions, gaps will open for the outer Fermi point. So if you, here is your Fermi level. So this outer Fermi points here will develop some gaps due to the presence of electron-electron interactions. And as a result, the inner Fermi points will constitute a synthetic helical liquid in that spin and momentum degrees of freedom around these Fermi points here are locked to each other. We have also looked to the same kind of system, but now in the proximity of a S-wave superconductor. And we have found that in this case, the helical liquid phase, on top of the helical liquid phase, there will be a P-wave superconducting phase. So the blue region in the phase diagram that you see over there, and this is a topological superconducting phase with Majorana zero modes, one at each end of the wire. Okay, I have to. Yeah, that. Oh, now we have three. Yeah, that's the one. Let's unplug this. Let's see. Now there. Okay. But now let's go back to our previous model without electron-electron interactions, without superconductivity, the most simple Hamiltonian that we have seen before. And you can understand this kind of system as a chain. Here you see one of the unit cell. So in this kind of model, my unit cell will have R sites, where R is the inverse of the wave number of the external modulation. In the upcoming results that I'm going to show you, I'm going to take R equals 4, so 4 sites inside the unit cell. And each site in the unit cell has attached to it spin. So basically the Hamiltonian, when we rewrite a little bit, we see that the Hamiltonian has spin conserving and spin flipping hoppings, this alpha and beta hoppings that you see here. They can be rewritten in terms of the original microscopic parameters in this way. From now on, I'm going to take all of the parameters fixed, and only this highlighted parameters phi, which is the phase shift, theta, which has to do with the ratio between the Dresselhaus and Rashba spin-orbit couplings, and this gamma effective, which also has to do with Rashba and Dresselhaus coupling. So I'm gonna construct a phase diagram for this kind of system in terms of these three parameters. But before that, I have to rewrite my Hamiltonian in K-space, which can be done because without electron-electron interactions, I can diagonalize the Hamiltonian in K-space. And this is the Bloch matrix that arises, which has this form. It's written in terms of this Q matrix, which is 2R times 2R. And here, this A matrices are little 2 by 2 matrices, which are written in terms of those alphas and betas, which are, again, the spin-conserving and spin-flipping hoppings acting throughout my lattice. And by doing that, I'm able to characterize the symmetry class of my Bloch Hamiltonian. And for those who are not very familiar with the tenfold way, here I just give a very, very brief explanation of what that means. It means to characterize the Hamiltonian in terms of chiral, time reversal, and particle hole symmetries. In other words, this if your Hamiltonian has such symmetries, it means that it is invariant under such relations, where S, T, and C are the chiral, time reversal, and particle hole matrices, respectively. And in our case, we have all three symmetries, and for our Hamiltonian, the corresponding chiral, time reversal, and particle hole matrix are like so. And this puts us in class C2 of the Outland-Zimbauer classification. And in class C2, and one dimension, the system can be characterized by a topological invariant of Z type, which is a winding number. This winding number is a quantity that we can compute for this type of Hamiltonian. It has to do with the winding. It has to do with the winding of this Q matrix on the complex plane, not the winding of the determinant, which is a complex number. The way this complex number winds on the complex plane, winds around the origin. It is a quantity that we can compute. That's what we do. And we find this phase diagram. So this phase diagram, what's shown here, is the winding number of the model on the parameter space, gamma effective, theta, and phi, the three parameters that I showed before. And this winding number, which here I call W, takes 0 value on these chunks, on these big chunks here, which means that in this regimes in the parameter space, my system is a trivial gapped insulator. For the dotted regions, I have also a gapped system, an insulator, but a topological insulator. And these two types of insulators are separated by critical surfaces where the gap closes. And these critical surfaces come in three variations. Topological gapless, which are the blue sections here, where a modified version of the winding number takes on the values -1. And then you have the orange sections, where the is also topological gapless regions, but now the topological invariant, the winding number takes on value 1. And then there are the yellow lines, which are the intersections between of the critical surfaces, where the modified winding number is 0. If we look at the spectrum on, for example, if I choose a set of values exactly here on this blue sector of this critical plane, and I look at the spectrum of the system, it looks like this. So I have 8 bands, okay? And they exactly cross or touch each other at 0 energy, so the system becomes gapless. And we see that the way the system becomes gapless is through the formation of time reversal symmetric 0 energy nodes, which have linear dispersion around the points where the gap closes. And the topological invariant, the modified winding number, exactly at these nodes, is in this case takes on values -1 here and -1 here. So equal topological invariant. If I do the same thing, so if I plot the spectrum for a point here, now I have the same kind of spectrum, but now the topological invariant on both sides of this time reversal symmetric nodes is -1, and for a point exactly on the multicritical line, which is where the critical surfaces cross each other, the topological invariant, the modified winding number is 0. So here I show you that these nodes, for example, if you take a point here on this blue patch of this critical plane, and then you plot the spectrum for different values of theta. So let's imagine that we are going through along a line on this plane and varying the value of theta here. You see that these points, these nodes, they are movable. They're not fixed. They're not high symmetry nodes. They are actually movable throughout the Brillouin zone. And this reminds us of vial cones in 3-dimensional semi-metals, except that for vial cones, the monopoles carry opposite topological charge. And we have seen before that in our case, the topological charge, the topological invariant attached to these nodes have equal sign. So this is very interesting because vial cones are topologically protected, but only locally, because these charts, by varying a parameter in the Hamiltonian of a vial semi-metal, you can make this topological charges come on top of each other and annihilate each other, and the gap opens. In our case, what we are seeing is something similar in the sense that we have movable nodes in the Brillouin zone. However, they carry the topological invariance of opposite signs, which are here working effectively as repulsive topological monopoles. So that these nodes can never pairwise annihilate. It's like they are repelling the center of the Brillouin zone, and the extremities of the Brillouin zones are actually forbidden places for these monopoles. They never meet up here and annihilate due to this repulsive character of the topological monopoles in this case. So different from what we have with vial cones, here we have global topological protection in that these nodes can never be undone by through pairwise annihilation. There's also something important to mention, which is this critical plane here, which is defined by this parameter phi being pi/4, is actually attached to an extra enhanced symmetry of the system. So on top of the tenfold way symmetries that I have mentioned before, when phi becomes exactly pi/4, another symmetry appears in the system, which is a mirror symmetry. So there is a mirror point in the chain. And the presence of this enhanced symmetry means that this critical plane here, which is labeled by A, defined by phi being equal pi/4, is symmetry enforced, different from these curved surfaces here labeled by B, which are accidental. So the nodes that appear, in both cases, the nodes are topologically protected, but only on top of this plane A, they are also symmetry enforced, whereas the nodes on surfaces B are accidental. Okay, and that leads us to another topic regarding this phase diagram, which is the type of phase transitions that are allowed. So we see here that we have basically three types of phase transitions. I can go from a trivial insulator to a topological insulator through the critical surface B or through the critical plane A, but I can also go from trivial to trivial or topological to topological, crossing exactly at the critical, multicritical line, this yellow line. And these kind of transitions are very intriguing in that they are neither symmetry breaking nor they are topological, because the topology on both sides and the symmetry of both sides of the multicritical point are the same. And if we look at the ground state energy for, say, a topological transition connecting a trivial and a topological insulator across plane A, so this here, in the inset here, you see the ground state as a function of parameter phi, the first derivative and the second derivative for increasing number of unit cells. So you see that exactly at the critical point, there is a very sharp response, signally the occurrence of a normal second order topological phase transition as we expected it to be. If we plot the same kind of thing for a transition across the critical surface B, we see a very sharp response at the second derivative of the ground state energy. Again, this indicates the expected second order quantum phase transition. However, if we look at, say, a 2-2 type of transition, a transition connecting a topological insulator to and another topological insulator. Here you see the ground state energy, first derivative, second derivative, third derivative. Only at the fourth derivative, there is the tendency to a non-analyticity. So we see that the peak becomes sharper and sharper for larger systems, indicating that at the thermodynamic limit there is a non-analyticity, but only at the fourth derivative, suggestive of a fourth order transition. If we look at the gap, how the gap closes, so this here's a color code for the gap on top of the theta phi parameter space, and yellow here means 0, so that's the gap closing lines. Here's the multicritical point, which is the intersection of these two lines. So if you're far away from the multicritical point, you see that the gap closing is pretty conical, so linear. But exactly at the multicritical point, if you plot the gap profile as a function of, so if you're along a diagonal line here and you plot the gap profile, you see that it has a parabolic behavior. If you do a little bit, if you adjust the data to curves here, you see that in fact the gap critical exponent is close to 2. So this means that the proximity to the second order conical phase transitions here is forcing the gap to close, but in a softer way, so less sharp than it closes for the second order topological quantum phase transitions. It's almost like the gap doesn't really want to close, but it's forced to close because this is the crossing between two critical lines. So you could see this as a failed avoided level crossing. So typically the bands would like to avoid each other because there's no reason for a phase transition. But here this avoided level crossing fails because there are critical lines which cross and then forces the gap to close at this point. But you see that the gap closing is parabolic, which is softer than the conical gap closing of the second order topological phase transitions. So there are some scenarios that one could visualize to explain this kind of anomalous transitions. A possibility is that there is a hidden symmetry which is in fact spontaneously broken in one side of the multicritical point, or there could be a new topological invariant, not the winding number that we have computed, but a new one that would be able to distinguish between these two phases at opposite sides of a multicritical line. However, these two scenarios can be ruled out from very basic fundamental grounds, and a very quick explanation for that is that the ground state of the system, of this model, is unique. So there is no way that there is, even if there are hidden symmetries, they cannot be spontaneously broken by non-degenerate ground state. And this is also the fundamental reason why we can rule out the existence of a new topological invariant, in that it would also require some kind of hidden symmetry that would create subclasses in the Outland-Zimbauer classification in the tenfold way. But again, from the very basic fundamental reason as before, we can rule out this scenario. So this leaves us with the necessary conclusion that the gap is closing and the ground state energy is becoming non-analytical without a phase transition. This is quite it goes against common wisdom that says that whenever you have gap closing and non-analyticity in the ground state energy, this is a signature of a quantum phase transition. But in this case, we have both, but the two chunks at opposite sides of the point where this happens are the same phase. And this is occurring due to proximity to topological quantum phase transitions. So it's proximity-induced gap closing and non-analyticity without phase transition, but due to nearby topological quantum phase transitions. And with this, I thank you for your attention. These are this is the summary of my talk. So we have seen that a multiband chain that has both modulated Rashba and Dresselhaus spin-orbit interactions has a rich topological phase diagram that allows also for the appearance of multicriticality. In this kind of phase diagram, we have seen that the critical surfaces support movable zero-energy nodes with global topological protection. So these nodes that carry topological invariants of equal sign, and they repel each other so that they can never pairwise annihilate, unlike vial nodes in three-dimensional semi-metals. And we have seen that the phase transitions across a single critical surface are of second-order type, as expected. However, transitions across a multicritical line are very weird because they connect regions of the same symmetry and topology. And we explain this by the argument of proximity, saying that the proximity to the neighboring topological transitions is forcing the gap to close, along with non-analyticity of the ground state energy, but this is happening within the same phase. So thank you very much for your attention.
Thank you, Mariana, for the talk. Questions, everybody? So I have one. So one of the angles is actually given by the ratio between Rashba and Dresselhaus.
Yeah.
Is this the theta angle? Or I forgot, actually.
Theta.
Or, yeah, it's theta. So could it be that the transition is related to the dominant contribution being either